Hello, everybody. So here is our first actual lesson for this distance learning experiment that we're conducting right now. Um, we're going to be doing section 11.8, or at least we'll get through a lot of section 11.8. I'm not sure how we'll feel about that moving forward. I might have to check in with you guys again on Thursday and see how we are doing with this. But here we go, section 11.8, which is power series. And you can see what a power series is on the screen right now. It says we got the sum of terms. And the thing that distinguishes this from what we have been doing is that we've got this x to the n power. A power series is a series that can be written in the form basically something plus something times x plus something times x squared plus something times x to the third to the fourth to the fifth, et cetera, et cetera. You can think of this like a polynomial, except it's an infinitely long polynomial, and the coefficients don't necessarily need to be integers, which technically means that it is not a polynomial, but we can think of it kind of like that. Something plus something x squared is a power series. We'll start with a very simple power series if all of the coefficients are exactly 1. So we've got the sum as n goes from 0 to infinity of 1 times x to the n power. So 1 plus x squared plus x cubed, etc., etc. And this should look familiar. This is not the first time that we've seen this one. It's been a while since we saw it, but we've got a series that looks like this. And when we looked at this last time, we identified that this is actually a geometric series because the ratio between each terms, or between each of the sets of terms, is x. X is x times as big as 1, and x squared is x times as big as x, and x cubed is x times as big as x squared. And so since this is a geometric series with a ratio of x, the sum of this series is the first term, 1, divided by 1 minus the ratio, and the ratio is x. And so we can actually take a look at this series on Desmos. If I start typing a few of the terms, y equals 1, there's the first term in red, the horizontal line, because all it is y equals 1. But then when I add the next term, y equals 1 plus x, now I've got a line with a slope of 1 and an x-intercept of 1. Add the next term, x squared, and now I've got a parabola plus x to the third power. And instead of typing each of these terms, you can see that I've got some other stuff set up over here. I'm going to get rid of that and say that that's what this is going to do. I've got a function defined as the sum of x to the n as n goes from 0 to some number, and that number is determined by this slider over here. So right now it's just, well, it's not displaying anything. Now it's displaying y equals, or f of x equals x to the 0, which is 1, and then 1 plus x, 1 plus x squared, 1 plus x cubed. And I'm going to start speeding this up so you can see what happens to the shape of this graph as I add more and more and more and more terms. Now we can see that at first it changed quite a bit. And as I do this more and more, the tail end over here is flipping up and down, but you didn't see a whole lot of change happening over on this side at all. Now, my claim is that this is a geometric series with a ratio of x, which means it should fit really well with this y equals 1 over 1 minus x that we claimed that it was equal to. And I'm actually going to go through that process again so we can see how it starts off as the horizontal line. And as I add more and more and more terms to this, it fits better and better and better and better, at least on that interval. The interval being between -1 and 1, because that's where this geometric series is going to converge. When the ratio is between -1 and 1, we see that this is fitting really well for values that are close to 0. As we get closer and closer to -1 and +1, we can't really see it because it's way up off the top of our screen. But the more terms we do, this is only 30 terms. And so if I did 50 terms or 100 terms or 2,000 terms, this would fit closer and closer and closer. But then outside of the -1 to 1 range, it doesn't look anything like it. This stuff over here, it is never going to approach. The stuff that's happening over here on the other side of the vertical asymptote, it is never going to approach that over there. And so that is our first power series. If I say, what about this one? This one looks awfully familiar. It's basically the same thing, except I replaced the x with an x plus 4. And so we can even think back to what you learned in pre-calculus. If I replace the x with an x plus 4, it's going to do a transformation. It's going to take exactly the same graph and move it 4 units. We can see there it is. It's the same graph as the black graph. And you can see when I do 30 of these terms, it's dragging my computer to a halt. So I'm going to cut that down to, let's go to maybe 10 terms will be good. We can see mirror images. The purple graph and the black graph are the same thing, except one has been shifted over by 4 units. And so that is also a power series. That's what that one would look like. And we can kind of see what the behavior of both of those graphs are. More on this in just a moment. The next bit of notes talks about where these power series converge. And we'll take a look at each of these 3 examples before we're done with this lesson. But it is true that for no matter what kind of a power series you've got, if it's in this form, something, some coefficient times x minus some value, this is just going to give us that horizontal translation, move the graph to the left or to the right, to the n power. There's our general power series form. There are only 3 possibilities for where this graph is going to converge, or where this series is going to converge. It may only converge at that specific point, which if you take a look at this, if x is equal to a, if x is equal to a, x minus a is 0, and you've got the very boring series 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0, which technically converges, but that has to be a case that we consider. Second case is that it converges for all x. We'll see one of those before we're done here today. And then finally, the third option is the one that we saw already with the geometric series. It converged between -1 and 1. There's a radius of convergence. It converged around x equals 0, or converged around x equals -4 in the case of this graph over here. And then we had a radius of convergence around that. If we're within 1 unit of 0, it will converge if we do enough terms. And the same thing over here for this graph. The center of the convergence is at -4. And if I go 1 unit to the left or 1 unit to the right, the more terms we add, I'm going to let my computer get dragged to a halt here again. But as it slowly but surely shows up, we see that it's getting closer and closer. The more and more terms we have, the better this series will converge on that interval. And so those are the 3 possibilities: only at the center, everywhere, or on some interval around that center. So I'm going to compile all this information. I've got actually quite a few of these functions for us to take a look at. I'll probably get through just a few more on the video before I cut myself off and leave some for you to do. But when I say um, where is this converging? What is the interval of convergence? I'm going to say that the radius of convergence is simply, well, the distance from the center to the edge of convergence. Oh, why is it doing that? And so my radius in this case is just 1. For both of these functions, it was just 1. But then my interval of convergence, I'll say this was from -1 to +1. And then for the one that was shifted over by 4, this was going from -5 up to, let's see, that must have been going to -3. I'm putting parentheses on here because at those endpoints, -5, -3, or -1 and 1, we would have an alternating series that has terms that are not going to 0, so it would not converge for those values. The next example I'd like to take a look at is this x to the n over n factorial. So if we listed a few terms of this, we would have x to the 0 over 0 factorial. Reminder that 0 factorial is defined as being 1. So I've got x to the 0 over 1, 1 over 1, which is just 1. The next term would be x to the 1 over 1 factorial, so x. The next term would be x squared over 2 factorial, x to the third over 3 factorial, x to the fourth over 4 factorial. And I want to take a look and see um, where this is going to converge. And so this isn't a geometric series. I can't just look at the ratio or something like that, which means we are going to go to something that we have been doing before break. Now I took the liberty, I just wrote this one out on paper and scanned it so that you wouldn't have to put up with trying to watch me write with my mouse. But here's how the ratio test works. A reminder of how the ratio test works. It's the limit as n goes to infinity of the n plus first term divided by the nth term. I've already multiplied by the reciprocal instead, like we did after trying a problem or two. I do have absolute value brackets on this one. For a lot of problems, it doesn't matter, but because x could be positive or negative, I cannot ignore the absolute values on this one. So I sent it through the process, little simplification, little rearrangements. I put the factorial terms together. I put the x to the power terms together, and then did some simplification so I can cancel. X to the n plus 1, I've got x to the n, and then 1 more x. N plus 1 factorial is n plus 1 times n factorial, which lets me do some canceling out of those terms. And I'm left simply with the limit of the absolute value of x over n plus 1. My claim is that this is less than 1 for all values of x. N is going to infinity, and so this denominator is getting really, really big. And so no matter what the value of x is, even if x is 10,000, eventually that denominator is going to be bigger than whatever that value is. So you pick a number, any number for x. Eventually the denominator is going to get bigger than that, which means this fraction is eventually going to be less than 1, or at least the absolute value has to be less than 1. So what this means is that this series will converge for x on all real numbers. This will converge everywhere. And I'd like to show you what that looks like when I've got a series that converges everywhere. So I'm going to turn these off and put the number of terms back down. And then let's see, this is the series that we're looking at. So here is just y equals 1, y equals 1 plus x, y equals 1 plus x squared over 2, plus x cubed over 3 factorial, plus x to the fourth over 4 factorial. And then I'll start to let these terms go. And we see that unlike the previous one where it appeared to have kind of a cutoff where it wouldn't keep converging after that, this one just keeps on going. The more terms that I add, it just converges farther and farther over to the left side. And on the right side, we can't even see what's going on because it's way off the top of the screen. But that's what it looks like if it's converging, not just at a point, not just on an interval, but this one is converging everywhere. The more terms I add, the more it's converging, getting farther and farther and farther away. Now the question is, what is it converging to? Or, sorry, grammarians, to what is it converging? So for a little hint as to what it's converging, in what direction it's converging, let's take a look at the series written out like this. And I will ask you, what is the derivative of this series? If this is my y, then what does my y prime look like? And y prime, well, the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared over 2 would be 2x over 2, which simplifies to x. The derivative of x cubed over 3 factorial would be 3x squared over 3 factorial, but 3 divided by 3 cancels out the 3 and leaves us with just 2 factorial in the bottom. Some light bulbs are going off. Hopefully, as you're watching this, the derivative of x to the fourth over 4 factorial is 4x to the fourth, 4x cubed over 4 factorial, but the 4's cancel out, leaving us with 3 factorial, and maybe you're starting to see what's happening here. The terms are identical. This is a function that is its own derivative. And if you don't believe me, do a few more terms, but you will see that this is going to keep going in the same pattern. This is a function that is its own derivative. So if I graph another function that we know that is its own derivative, y equals e to the x, as I put a few terms of this, we see that yes, it is converging, and it is converging to the function y equals e to the x, which is a surprising result, maybe. An interesting result, I would say certainly. We see it starts to diverge over here, but that's only because I've done only 30 terms. The more terms that I do, in fact, I suppose I could do this. If I go up to 50 terms, we're going to see that it continues to converge beyond what I can see on the screen. And so 50 terms sticks with it even longer. Of course, it eventually goes away from that, but if I added more terms, we could have it converge for as long as we want. And I would be scrolling like this for quite a long time to try to figure out where it's diverging on the top end. But suffice it to say that there we go, that series, um, given what we saw with the ratio test, this tells us because this limit was less than 1, we know that it converges everywhere, all values of x. So when I say what is the radius of convergence for something like this, I can say that it's an infinite radius. We could say from negative infinity to infinity, or maybe I'll just say that this converges for all real numbers. My interval of convergence is all real numbers. And then finally, I'll finish up with this one. A series that's similar. It looks kind of similar. It's got the same types of terms, but this one's going to have very different behavior. N factorial times x to the n power. And I think the best way for me to do this is to just show you what this one looks like. We've seen the behavior, how a series behaves if it converges on an interval. I'll just put that one up here again so we can see what this looks like, if my computer would catch up with me. So converging on this interval between -1 and 1, we saw what happens when I've got a series that converges everywhere. It just keeps on getting wider and wider as I add more and more terms. And then we've got the behavior that's going to happen on this one, the sum of n factorial times x to the n power. And so just pay attention to what's happening as I add more and more terms. We see that the interval over which it is converging is getting smaller and smaller and smaller. Instead of getting bigger and bigger, it gets smaller and smaller. And it's going to take a little while for it to catch up with me. I think the interval ends up being just this little tiny interval in here. I don't think it's even caught up with me yet, because I think it should be just a little bit smaller than this. Or maybe my computer is just going to quit on me at this point. Oh, there we go. So just that little interval, and that's with only 50 terms. As I add more and more and more terms, this gets smaller and smaller and smaller. It will converge at x equals 0 because the series is just 0. But what's happening here is that n is getting really, really big. It's overpowering anything that the x to the n power would be doing. And so if you send this one through the ratio test, and I encourage you to do this, try out the ratio test on your own just to try this out, compare it with what we did with the previous one, and you'll find that no matter the value of x, the value of the limit is only less than 1 when x is equal to 0. So I don't know if it fails the ratio test, but the ratio test tells us that there is no radius. This only converges at x equals 0. I'll maybe just say x equals 0 is the only place where this one works. And I think that's where I'm going to stop what I'm doing here. I'm going to let you guys take a look at these two, certainly this one. I'm going to leave this for Thursday for us to talk about. One thing that I'm ignoring right now intentionally, because I don't want to overwhelm you guys too much, but one thing we need to take a look at is when a series converges on an interval, how do we determine what the endpoints of that interval are? For the one that we looked at already, the geometric series, we knew based on what we've talked about with geometric series that it does not converge at the endpoints. But the example I have here next, this one, if you want to take a look at this one, send it through the ratio test. You're going to get an answer. You're going to get a radius of convergence, but we're not going to be sure about exactly where on those endpoints it converges. But again, I'm worried about overwhelming you at this point, so I'm going to stop here. You should be able to start working on the 11.8 assignment, but you will not be able to finish it up. I'm going to have that one be due on Friday. Reminder that we're also going to have a quiz on Friday, not on this, but on the test for convergence that we've done already, similar to those multiple choice questions that we looked at. Well, I'm not sure if you looked at them before you watched this video or if you looked at them after you watched this video, but the multiple choice questions, does this converge or does it not converge? That quiz will be on Friday. As always, certainly give me any feedback that you want. If you want to send it to me through email or drop me a message in the Google Hangout, or if you have any suggestions about other ways that we should be communicating, certainly get in touch with me about that. Otherwise, I will touch touch base with you guys again on Thursday. Enjoy your Wednesday of relaxation while I'm trying to figure out what the rest of this week is going to look like. All right, take it easy. Bye.